start recording, and the stage is yours.
Okay, hello everybody. Thanks for those of you who were here last week coming back again, and anybody new, I hope I say something interesting. So I'm just going to continue the story from where I left off last week, and just to remind you where that was, I had described the results of a number of experiments that had collectively led us to understand that neutrinos were not as they had originally been described in the standard model, that neutrinos, even though they might be created in some pure flavor eigenstate, like a muon neutrino or an electron neutrino, wouldn't necessarily stay in that eigenstate. And then furthermore, they must have mass, which is of course not true in the standard model. So now to continue the story, I'm actually going to go back a bit, because there are several parallel strands that went along in this story. And I wanted to finish the sort of solar neutrino bit of it. But while that was all going on, the Kamiokande experiment and the super Kamiokande experiment, which I described last week, describing what they did as solar neutrino experiments, were actually doing the other half of their physics program, or another part of their physics program. It wasn't halves. I mean, Kamiokande, while this was going on, was also discovering neutrinos from supernova 1987A, which won Masatoshi Kashiba, who is the fellow who led the building of it, the Nobel Prize. So, various other things were going on that I haven't had time to talk about, but they were pursuing their other major physics program, which was to search for proton decay. So, what is proton decay? Well, in models of physics beyond the standard model, if you just do the obvious next thing, so you've combined electricity and magnetism to make electromagnetism, and then you combined electricity, magnetism, and the weak force to make the electroweak force, and kind of the obvious next thing to do is to combine those with the strong force and make some grand unified model of those. And people were working on that back in the 70s and 80s. And the obvious implication of that sort of thing would be there would be some new interaction that would couple quarks to leptons, and it would mean that a particle made of quarks could decay into particles made of leptons that were lighter. And so that would mean the proton would not be stable, the proton would decay. And so as a way to gain insight into this physics, people look for proton decay. And in the case of super Kamiokande and Kamiokande before it, you have just these big tanks of water. The lifetimes that were of interest were of 10 to the 30 to 10 to the 32 years. Of course, for comparison, the universe is of order 10 to the 11 years old. So, this is a very, very long time. And even the most patient graduate student is not going to watch a tank of water for 10 to the 32 years. But you can get a tank of water with 10 to the 32 protons in it. And if you do that and you watch it, then one of them should decay. And the preferred mode for most theories is that a proton should turn into an electron and a neutral pion, or a positron actually, and a neutral pion. And the neutral pion will immediately decay to 2 gamma rays. And what you get is a back-to-back signature with a positron in one direction and 2 gamma rays in the other direction. And each of those would produce a ring in these water Cherenkov detectors. So you look for this signature with 2 rings on one side, 1 ring on the other. Now, like any rare decay experiment, the first thing you think of is, well, what's the background? Well, the background has to be something that can get into the middle of 40-meter in diameter tank of water without leaving any signal, right? And so that rules out all the particles in the standard model except for neutrinos. And so you worry for your background, is there a source of neutrinos that would go inside my detector and interact, potentially producing a signal that might look like a proton decay? and the mass of a proton is about a GeV. So you worry, is there a source of GeV neutrinos in the world? Well, unfortunately, there's a very intense source of GeV neutrinos in the world, and that is the neutrinos that come from cosmic ray interactions. Now, as you know, the Earth's atmosphere is constantly bombarded with high energy protons and other nuclei arising from very energetic processes out there in the galaxy and beyond. And these collide with molecules in the upper atmosphere. And when a proton or another nucleus of very high energy collides with nuclei, the result from that is a shower of pions. And these pions decay. So a pi plus decays to a mu plus and a nu mu. And the mu plus then decays to a positron, a nu mu bar and a nu e. And these neutrinos are what we call atmospheric neutrinos. They're neutrinos arising from cosmic rays in the atmosphere. The ratio of them you can see from this decay chain should be 2 nu mu's to 1 nu e. And that's quite a robust prediction. Sort of nothing you do in theory changes that prediction very much. There should be 2 nu mu's to every nu e. And the flux seen from inside the atmosphere should look symmetric, more or less. If you assume this on the left is all that happens, then the flux should be completely symmetric, sort of for the same reason that the gravitational field vanishes if you're inside a sphere. It balances out in all directions. The stuff that's farther away, right, there's also more of it, and it completely balances out. You should see an isotropic flux of neutrinos, 2 nu mu's for every nu e. And these neutrinos could go inside your water Cherenkov detector and produce background, and perhaps that background will look like proton decay. So on Super Kamiokande, the guy in charge, Yoji Tatsuka, set his best graduate student, Takeaki Kajita, the job of studying in great detail this background. And so Kajita-san, being given the less glamorous task of studying the background, proceeded to do so. And to cut along, now, this is just a plot just to show you that indeed atmospheric neutrino events can produce signals that kind of look like proton decay. This event happens to be from the SNOW experiment rather than from Super Kamiokande, but you can see this is an atmospheric neutrino event in SNOW, and you can see there's one ring and here's another, right? So there's 2 of your 3 rings that you want to that you're worried will look like a proton decay. So clearly you can produce such signals. When Kajita-san examined the signals that he saw in Super Kamiokande, now remember, Super Kamiokande, as I told you last week, is a very good detector for observing neutrinos because it is huge and yet has very high effective granularity of all those phototubes. Just to remind you, Super Kamiokande is where'd it go? Oh, sorry, I must have left it out. It's just a right circular cylinder, 40 meters high and 40 meters diameter, like the world's largest Coke can, filled with 50,000 tons of water and surrounded by 11,000 50 centimeter in diameter photomultiplier tubes. Now these photomultiplier tubes completely tile the surface. You'll see a picture in a bit, or actually I went over a picture a minute ago. And each one can detect a single photon of light. And so when a neutrino interacts within the detector, say a nu mu will produce a muon. That muon is traveling faster than the local speed of light. So it will emit Cherenkov radiation, which goes in a cone out from the muon. The muon slows down and stops. So that cone produces a donut of light on the surface of the detector. So what we do here is we take the Coke can and we take the top and the bottom of it and open them up. So that's the top of the detector and that's the bottom of the detector. And then you cut the Coke can down one side and roll it out flat. And thus you project the inside of a Coke can onto a flat surface. And that's what it looks like. And each of these dots is one of those phototubes having been hit by a photon. And this nice sharp ring is characteristic of a muon. If an electron neutrino interacts within the detector, electrons are light. So as they're going through the water, they multiply scatter. And so their ring goes bouncing around and gets fuzzy. And so nice sharp rings are muons and fuzzy rings are electrons. And it has been confirmed with beam tests at the KEK, the Japanese Accelerator Laboratory in Tsukuba, that one can tell electrons from muons, correctly 99% of the time by distinguishing fuzzy rings from sharp rings. So Kajita-san proceeds to look at the muon and electron neutrino backgrounds, and he should see 2 muons for every electron. And lo and behold, he doesn't. Here is a plot, very famous plot. As I'm sure most of you know, Kajita-san got the Nobel Prize for his study of the less glamorous background in the detector. And the poor guy who did the more glamorous study of proton decay didn't find any and is still working hard. Well, he's now the spokesperson of the successor of superchemia Kando, which is called hyperchemia Kando. I'll come back to that later. So here's this is not the data from his thesis, which was done back in the days when we still scribbled stuff on pieces of acetate. I have those plots, I should put them up. But anyway, this is a nicer one from later, shows the same thing. These are electron-like events, fuzzy rings. These are muon-like events, sharp rings. They're plotted as a function of cosine of the zenith angle, right? So 1 means a particle coming straight down from over your head, and -1 means a particle coming up from below, and 0 means a particle coming sideways from the horizon. And if you look, the muon, the electron-like events, okay, look like what they're supposed to look like. The Monte Carlo, the prediction is the blue boxes, and the data are the points. And lo and behold, the points look like the blue boxes. So everything's okay for electrons. For muons, though, not true at all. The muons coming down from above, the points fit really well, and so things look okay for muons coming down from above. But for muons coming up from below, they're missing, right? There should be, they should look like the blue boxes, and you note the blue boxes, there's about twice as many of those in the muons as electrons. That's the 2 to 1. But in fact, and the fact that it's not exactly 2 is down to efficiencies and some other things I don't want to go into. The muons coming up from below seem to have disappeared. About half of them are gone. And if you fit that to the idea that the muons have oscillated, that the initial muon neutrinos have changed into tau neutrinos as they traveled through the Earth, you get this red line. And as you can see, this is an excellent fit to the data. A cute thing is that this plot by itself proves that neutrinos have mass, right? That plot all by itself proves the standard model is wrong. And the reason is because the neutrinos traveling up from below know they have traveled farther than the neutrinos traveling down from above. Well, how do they know that they have traveled farther? Well, they don't know how much material they've gone through because they're interacting too weakly. So the only difference between these coming up from below and these coming down from above is how long they've been traveling. So they know how long they've been traveling. And that means they have a clock on them that isn't stopped. And a particle traveling at the speed of light, a massless particle has to travel at the speed of light, their clocks are stopped, right? And so this plot by itself shows that neutrinos have mass, or that Lorentz covariance is violated, or special relativity is broken, one or the other, right? You can take your pick, but we tend to believe that neutrinos have mass. So that was cool. And when combined with all those other experiments I told you about, and a few more that I haven't, it proves that neutrinos oscillate. And okay, so this is an interesting thing. And what we would like to do is probe this in detail and try to measure more, more accurately the behavior of the oscillations. What is between the mass eigenstates? Is it nu mu to nu tau, or is it nu mu to nu e, or is it some mixture of the two? And however, we can't get a lot more out of this because we don't have any control over the neutrino source. It's just cosmic rays. And so we can only model that so well, and we can't control it, we can't change it, can't alter the baseline, can't change the energy. We're just stuck. And so in order to improve this, we would like to do this. Now, 1 GeV, that's an easy energy to reach with a terrestrial accelerator, right? And so if we're interested in, few GeV neutrinos, that's something we can make. So in principle, we can do our own neutrino oscillation experiment. We don't have to rely on nu mu's from the atmosphere. We can make our own nu mu's and do an oscillation experiment. And so to tell you about such oscillation experiments, I'll start with some ancient history, because there's a cute little thing in here that, a cute little counterfactual. The world could have been a very different place if these parameters were a little different. So let me explain that remark. So let's talk about some ancient history. In the late 1950s, neutrinos were known to exist, and they had been seen from 3 basic kinds of reactions. There were neutrinos that arose from beta decay. So, the prototypical beta decay, neutron goes to proton plus electron plus neutrino. And this could be a heavier nucleus. Neutrinos were seen to be emitted by pion decay. Pions decay to muons in a neutrino, right? And neutrinos were observed to arise from muon decay. Muon goes to electron in 2 neutrinos. And why did they think this was 1 and this was 2? Because when the pion decays, the muon always has the same energy, right? And so that tells you it's a 2-body final state. When the muon decays, the electron has a range of energies, and that tells you it's a 3-body final state. In neither case do you see anything other than the muon or the electron in the final state. So you know that this one is a 3-body, where the other things in the final state must be neutrinos. So you have these 4 different neutrinos that have been observed. And the question was, well, are they the same thing, right? And if the answer is yes, that there's just one particle called the neutrino, and all of these things are it, then why don't you see muons decay to electrons and photons via a diagram like this? Where in the late 1950s, when they drew this diagram down, I took this from a paper by Fermi, when they drew this diagram, they called this thing an IVB, or intermediate vector boson. We would now call it a W, right? I mean, even though they didn't have the standard model, they knew what kind of underlying form that the weak interaction would have to have. And they knew it would be carried by a spin 1 electrically charged boson, in which they called an intermediate vector boson. And if you had that, then you ought to be able to draw a diagram like this. And so muons should decay to electrons and photons. But experiments had already been done looking for this decay, and it wasn't there. And we still look for this decay, and we still haven't seen it. Okay, and although we're sort of 12 orders of magnitude more sensitive than they were back then, we still haven't seen it. So a speculation arose that was because these neutrinos carried a lepton quantum number. There were electron neutrinos and muon neutrinos, and only muon neutrinos could make muons, and only electron neutrinos could make electrons. And if that's true, then this diagram is eliminated. You can't have this diagram because that neutrino is emitted as a muon neutrino, but it has to be absorbed as an electron neutrino. So I'd have to change from one to the other. And so they say, well, maybe that's true. So an experiment was done to test this hypothesis. And it was done at Brookhaven. This is the AGS, the alternating gradient synchrotron at Brookhaven, by these guys, including Letterman and Steinberger. So Leon Letterman became the director of Fermilab. He was director for many, many years. and Jack Steinberger was an absolute institution at CERN. And always at CERN, anytime you went to CERN, you saw Jack, and he would grumble at you. He was not one of life's natural bubbly characters, but he was a brilliant physicist. And anyway, this is the experiment they built. It kind of sounds like they're just doing what the atmosphere did. So they take protons from the AGS, they collide them with a target, that makes pions. They had a big bag of helium here, which is kind of poor man's vacuum, and let the pions decay. The pions decay to muons and nu mus, or well, muons and neutrinos, note that point. The muons are ranged out in this material, which is actually the chopped up armor from a World War II battleship. There was lots of, in national labs at that time, you could get, back then, you could have anything you wanted that was war surplus. And so they had a 16-inch naval cannon that was used as a neutron collimator at Fermilab in the early days. And then you hit a detector. The detector was a so-called spark chamber. It was just a set of parallel plates of metal. The plates were put at very high alternating electric charge. So there was a big electric field across the gap between the plates. When a neutrino would interact, if it interacted and made a muon, the muon would go in a nice straight line through this spark chamber. And as the muon went between the plates, it would ionize the gas. And since the spark chamber was held at a voltage such that it was right on the edge of breaking down, when this trail of ions from the particles went between the plates, it would break down and a spark would jump. That would cause a current pulse on the power supply, and that current pulse would trigger a camera, and it would just photograph the wire chamber. The one side was glass. And so you would get these photographs. And so you had a line of sparks. That was a muon. And as I said, just as in the case of superchemiocanda, electrons shower. They get deflected, they emit photons, those photons pair produce. And so rather than getting a nice straight track, you do get a track from the electron, but you also get all these other hits around it from the shower. And so when they calibrate the detector, they look, this just counts the number of sparks in an event. And from shower events, they expect lots of sparks. From muon events, not so many. And when you look at the data, there aren't very many. And if you do this carefully and quantitatively, you conclude that it is consistent with all of the events being muons, which at the time was taken as evidence that nu mus and nu es are not the same thing. And that's why in the standard model, we have electron neutrinos, muon neutrinos, and tau neutrinos, because it is observed that when a muon neutrino interacts, it always becomes a muon. In some sense, that's our definition of a muon neutrino. Now, the interesting thing about this is I'm about to describe a couple of long baseline neutrino oscillation experiments that are essentially just the same as this, right? Okay, they're bigger and fancier and cost a lot more money, and they sure as hell have, more than 2, 4, 6, 7 authors on them, but they're conceptually just the same. You collide protons with a target, you make pions, you focus the pions, they decay, they make nu mus, you allow the nu mus to propagate, you detect them and see if any have turned into nu es, right? So this was a neutrino oscillation experiment. And the fact that it didn't see neutrino oscillations is just luck, right? It turns out that the delta m squared, the difference in the squares and the masses between the electron and the muon neutrino, right, is too small for you to see oscillations on this baseline, right? But if the world were a different place, there's nothing that we know of that would have prevented that delta m squared from being several orders of magnitude greater than it is. I mean, it wouldn't render the world uninhabitable or, make atoms unstable or whatever. It wouldn't do really anything that we know of. So if we lived in a world where that was different, where that delta m squared was much bigger, then this experiment could have had neutrino oscillations, and they might have seen half nu e's and half nu mu's there, which they would have interpreted in their theoretical understanding to mean that there was no difference between nu mu's and nu e's, and they would have herring off completely down the wrong path. The standard model wouldn't have come about, and who knows what, who knows how long it would have taken them to work out that they were wrong, and that that the physics was very different than what they thought. So this was a lucky break. These guys, they won the Nobel Prize for this experiment, by the way. So, these guys came to the wrong conclusion, or well, they came to the right conclusion based on their experiment, but it could have so easily been gone the other way. So in order to turn this into an experiment, a modern long baseline experiment, you just need two things that they didn't have. The first is they just collided protons with a target and just hoped that some of the pions went in the right direction, right? Well, you can't do that. If we want to see oscillations, we know we have to separate this detector from this target, not by, 10 meters as in this, but by hundreds of kilometers. And so we can't have our neutrinos just going in random directions, because the flux at the far detector would be much too small. So we need our pions to be pointed at the far detector, right? And to do that, we had to invent the neutrino beam. And that was invented at CERN in 1961 by a guy by the name of Simon van der Meer, who subsequently won the Nobel Prize because he was also the guy that invented stochastic cooling, which is what permits modern colliders to work. Then the other thing you needed are vast detectors. A set of spark chambers the size of a refrigerator, can't be your detector if your detector is 300 kilometers from your source of neutrinos. The detectors have to be vast. So this whole history is just a steady history of the detectors getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. The first really large one was built at CERN, the Gargamel bubble chamber. This was a giant bubble chamber, but subsequently they've gotten even bigger. This bubble chamber, by the way, made one of the most important discoveries. I would be comfortable with it being called the most important discovery in the modern history of particle physics, which is the discovery of neutral. Oh, there's Simon van der Meer. Yeah, when he passed away, there was an obituary in The Economist, and this photograph is from that obituary. And it went on and on and on about stochastic cooling, which is what the Nobel Prize for. And nobody seemed to notice that if you looked at what Simon van der Meer is doing here, he's talking to these gentlemen. And if you look at what's drawn on the whiteboard here, it's a horn magnet. So what he's describing is how you make a neutrino beam, not how you do stochastic cooling. So I'll skip over the discovery of neutral currents, which is a cute story in itself. But this discovery of neutral currents, this was the first confirmed prediction of the standard model. So, when they wrote the standard model down, people thought, oh, well, that's pretty, who cares? Is it right? Who knows? And one of the things it predicted is there should be weak neutral currents. There should be weak interactions that don't change the charge of the target particle. And these had never been seen, never even been imagined, and they do exist, and they were discovered in the Gargamel bubble chamber. And we'll come back because we need neutral currents to do some things in the experiment. So so now the major tools are in place. Now we got to do is just make them a lot bigger. So because in my talk to the joint physics societies some weeks ago, I talked about T2K. Just to be fair and to show there are many of you, I'll talk about MINOS instead, which is T2K's predecessor. MINOS was an experiment to fire a muon neutrino beam from Fermilab to an iron mine in upstate Minnesota in a place called Sudan. Okay, and the idea is straightforward. You You build a neutrino beam. I'll come back to the details of that in a bit. You fire it through a near detector. You allow it to propagate through 700 kilometers up to Minnesota, and you measure it in a far detector, and you see if the neutrino spectrum is the same in both. These detectors are a kind of detector that's used in a lot of these experiments, kind of a sandwich calorimeter. So what they are, they're plates of steel, and in between the plates of steel are planes of bars of scintillator. So there'll be a set of bars of scintillator that, with go running this way and running this way. And so a charged particle passing through this will hit, say that bar and that bar. And so by looking at where those two bars intersect, you get a point on the track of that neutrino. And then it propagates through a long, sandwich of this, and you can track the neutrino. This is iron, and the reason it's iron is because you pass a huge electric current through that wire, and that magnetizes the iron, which makes the charged particles produced by the neutrino interactions bend, so you can measure the momentum. So this thing was built. You're looking primarily for muons that give a nice track like this in the detector, and you can measure the momentum by the curvature. You may also get neutral current events, which in this case make a spludge, and electrons, which make a little shower. But MINOS was not optimized to look for these because people weren't interested in that yet. MINOS was built to look for these, and specifically it was looking for the disappearance of the muon neutrinos in the beam. Note that we have a very poor knowledge of the cross sections for all of these different things, which will come in later. And to cut a long story short, here is from MINOS. This is the energy of the neutrino, the reconstructed energy of the neutrino. The dots are the data. The red is what you would have expected to see in Minnesota, given what you saw in the near detector. And as you can see, the red is a very poor fit to the data. The blue is a fit assuming neutrino oscillations, and the neutrinos have disappeared. And lo and behold, it's a good fit to the data. And the plot on the right is just the same as the plot on the left, but you just divide the you divide what you expected by what you observe. So in the absence of oscillations, you'd get a flat line here at 1. Instead, you see this fit to oscillations, and these other curves are some other models. We won't go into the details. And so this looks like neutrino oscillations. And when you fit the oscillation parameters, which I haven't really talked about much yet, but that's the thing you measure in an oscillation. Remember that the formula for oscillations I showed you last time. I should have it here. Sorry, I should have put it up again. But it depends on the difference in the squares of the mass eigenstates, and it depends on the mixing angle. And when you look at that, you get this region, which is consistent with MINOS, and the blue and the red regions are what is consistent with that atmospheric neutrino data I showed you from Superchemia Canada. And so as you can see, this experiment has confirmed neutrino oscillations as the explanation. Is the same effect there in antineutrinos? Now, this is not something you can really do with atmospheric neutrinos because you get a mixture of neutrinos and antineutrinos in your data. You can't separate them out. But a Horn magnet only focuses one sign of pions. If your Horn magnet is set to focus positive pions, it defocuses negative pions and vice versa. So by which direction you flow the current through your magnet, you can choose whether your beam is neutrinos or antineutrinos. So that trick is used in MINOS and all other such experiments to make the measurement both for neutrinos and antineutrinos. Now, there's an unfortunate thing that will become very relevant later, which I should warn you about, which is it doesn't quite work. And the reason is if you really want the antineutrino beam and the neutrino beam to be just the same, you would need to collide an anti-proton beam with an antimatter target and change the sign of the current. But unfortunately, we can't make an intense enough anti-proton beam. We can't make an antimatter target. So all we can do is change the sign of the horn. And so that means we mostly change the beam, but we don't do it exactly. So in the case of Minos, there's not one, but there are two horn magnets, okay? And these focus the pi pluses and defocus the pi minuses. If I switch the sign and they produce, this is the spectrum that is produced, these are nu mu's, and you can see the nu mu bars are down here. Now there's still a few pi minuses that happen to be going straight down the middle of the magnet. There's no magnetic field there, so they don't get defocused. So you get rid of most of the wrong side neutrinos, but not all of them. And so you have your nu mu's and your nu mu bars. Unfortunately, when you flip the sign, you now focus the pi minuses and defocus the pi pluses. The problem is there's a lot more pi pluses and pi minuses. You're colliding protons with positive nuclei. There's a lot more pi pluses and pi minuses. So for an anti-neutrino beam, A, your beam is much weaker, this versus this, and B, your background is much bigger. Now, just remember that because it'll be important later. But given this beam, you can look for oscillations, and they do, and lo and behold, the parameters look the same. So, bingo. We've observed neutrino oscillations. Are we done now? No, you're never done. There are still unanswered questions. We don't know the pattern of the masses, and we don't know if the oscillations are the same for neutrinos and antineutrinos. As you can see here, they're not wildly different, but they could well be significantly different and be consistent with this data. And that's something we're very interested in because we're trying to determine if a difference in the oscillations of neutrinos and antineutrinos might contribute to the matter-antimatter asymmetry in the universe. And there's other things we want to know that you can't do with oscillation experiments, so I'll just skip on. And I mentioned this before, well, I mentioned this in that talk to the Joint Societies. The pattern of neutrino masses is related to the fact that we've only seen vacuum neutrino oscillations in the case of atmospheric and accelerator neutrinos. We haven't seen them modified by matter effects. And for vacuum neutrino oscillations, they depend on the sine squared of delta m squared, which means they're insensitive to the sign of delta m squared. So you don't know which of the mass eigenstates is a heavier one. So you get two solutions. You get that one and that one are both consistent with the data. Now, in the case of solar neutrinos, we have seen the MSW effect. So we do know that sign. So there's only two solutions here, not six. But you have two possible solutions. This one's called the normal hierarchy, two light and one heavy. This one's called the inverted hierarchy, two heavy and one light. Theorists tell us that this one is natural, and so that's normal, and this one's unnatural, and that's inverted. And my response, and so they expect this one. And my response to that is, you think this is natural and that's unnatural, right? Does that look natural to you? Okay. Nature decides what's natural, we don't, right? And so the question of what the pattern of neutrino masses is an experimental question. By the way, these same theorists who tell us that that's the right answer and that's the wrong answer also told us that the mixing angles would all be small. But if you go back and look at the plot I just showed you, right, the mixing is consistent with being maximal. Right? They expected it to be small. In fact, it's as big as it could be. So, you know, I always appreciate theoretical guidance, and then I always do the experiment, right? So how do we do that experiment? Well, here's the formula I reminded you of, right? But remember, there are 3 neutrino species, not 2. And this formula only takes into account 2 neutrino species. Now, many of you will have had to have derived this formula. When I was a graduate student, this was a rare and exotic thing. But now undergrads have to derive this formula in their undergraduate classes. You'll be happy to know that the next generation of students will not be sufficient for them to derive this, because we have to include the effects of 3 neutrino mixing, not just 2 neutrino mixing. And for 3 neutrino mixing, this formula considerably simplifies and it becomes this, okay? And even this is an approximation in that this is the formula in the case of constant matter density. Now, I don't have time to go through this. You could do a whole course just on the consequences of this hideously complicated formula, where each of these is a sine or a cosine of one of these mixing angles. And these are the various delta m squareds, right? And this delta is the angle that would violate CP. If this delta is 0 or pi, then CP is conserved. If this delta is anything else, then it's violated, okay? And the way you look for CP violation is you do the experiment with neutrinos, and then you do it with antineutrinos. And the effect of that is to change the sign of this sine delta term. For antineutrinos, this term changes sign. And so the overall probability changes by twice the size of that term, okay? The problem is, and in order to determine the mass hierarchy, you have to observe matter effects. Those are present, the MSW effect I told you about last week. Those effects are present in these terms with this little a in it, which is contains all those constants from the MSW effect. Now, the problem is this is a really complicated formula with lots of covariances and degeneracies. In other words, you measure one thing, the probability of nu mu to nu e, and it depends on, a gazillion parameters. So there's more than one combination of those gazillion parameters that will give you the same answer here, which tells you you can't do this with one experiment. You will need many. Okay, so the first thing we did was build T2K. I told the Joint Physics Society about this experiment. It's basically like Minos, but instead of the main injector at Fermilab, we use a proton accelerator at JPark. Instead of an iron calorimeter, we use supercameo-canda. We have to build near detectors to determine the properties of the beam before they propagate, and off they go. I will go through, I'm running out of time here, so let me skip the details. We use an off-axis beam, which is a clever trick to concentrate to build a beam and then miss the detector, which, believe it or not, concentrates the neutrinos at one energy, the ones you do get. Most of them then miss. So that's the beam on axis. If you go to off-axis angles, most of the neutrinos miss, but those that do hit, due to the kinematics, get concentrated as single energy. So if you put that energy right on the oscillation maximum, you get a more sensitive experiment. And we have our near detectors, which we spent years and years building, but I'll skip over this. I want to show you this plot, however, because this is one of the coolest plots that I have seen. I love this plot. When I tell people that we do an experiment where we have a accelerator on the east coast of Japan, and we collide a proton beam with a carbon rod, and that sits in a magnet, and that magnet points down in the ground, and then invisible particles that you can't see come out of it and fly all the way across Japan and then hit our detector that's the size of a 10-story apartment block buried underneath a mountain in Western Japan. They look at me like either I've been sampling the stuff that's sold at Grateful Dead concerts a little too freely, or I'm just nuts, right? And a reasonable question they ask is, how do you know this actually works? And this is my plot to prove that, okay? So T2K works by firing a neutrino beam from JPark through the near detectors and off to supercameo-canda, right, through the curvature of the Earth underneath Japan. at maximum depth, it's 1.7 kilometers underneath the ocean, underneath the mean sea level of Japan. Now, the accelerator does not produce a continuous beam of protons. That's not the way accelerators work. Accelerators work by bunching the protons into bunches and then accelerating them with RF cavities. And so there's an RF structure to the J-Park accelerator. It makes spills every couple of seconds. And those spills consist of 8 bunches. Each bunch is about 60 nanoseconds broad and separated by 540 nanoseconds when it's running in neutrino mode, or for neutrinos, which is when we do it. And so the neutrinos don't come continuously. They come every few seconds, and they have this comb-like structure. They're in 8 bunches, 60 nanoseconds wide, separated by 540 nanoseconds. So now let's go to the other side of Japan. Let's go to Super Kamiokanda, and let's take the events that we see in Super Kamiokanda and take every event and just plot the time of that event versus the time it would take a particle traveling at the speed of light to go from here to here if we start a clock at the time at the beginning of that spill. So we know when that is. We trigger a clock. We communicate via the GPS. We send that signal to J-Park, or to Super Kamiokanda, and we record that time. So now let's take all the events we see in Super Kamiokanda and bin them as a function of the time difference to that signal. And we see that here, okay? This plot, that line across there, is all the events, every single trigger of the detector. And what you see is it's almost flat because, you know, most of the events have nothing to do with our beam. But you see, even in the raw event trigger, you see a little bitty bump right there at 0. So those are events that arrive at the time you would expect something to come from J-Park. Now note, this scale is microseconds, and we're looking for things nanoseconds. So this is very broad compared to the beam. We'll come back to that. So now let me start throwing some events away. Let me look at only events which satisfy the low energy contained trigger. So these are events that have the right energy to be with from our beam and are in the detector, you know, contained in the detector. And that's this plot. And now you can see most of the events have been thrown away. And now there's a slightly bigger peak, right? Now let me apply another cut, which is to throw away all events that have any signal in the outer detector. I didn't show you, Super Kamiokanda is actually a can within a can. There's a thin layer around the outside that we have phototubes in that we use to throw away events where something's entering or leaving the detector. So those are events that come from cosmic, mostly cosmic ray muons. So we throw all those away, and what's left are these red events. And now you can see that, now note this is a log plot. So now you can see sort of 1,000 events at the time we expect to get events from our beam, and just 3 events outside of that. Okay? So that peak shows that something happens in our detector that knows what time we collided a bunch with a target on the other side of Japan. But that's not the cool plot. The cool plot is, now let me take this and blow it up to a greatly enhanced scale. I blow this up horizontally, and I get this plot that shows the time of the arrival of the events. And what do you see? There is the comb structure of the beam. The 60 nanosecond wide bunches separated by 540 nanoseconds. There it is. So the time structure of the beam is represented in these events which are detected 295 kilometers away after the particles have passed through the crust of the Earth across Japan. So that is the proof that what we're looking at are neutrinos from our target in J-Park. I love this plot. And then we look at those events, and lo and behold, what we see is when we look at neutrino events, what we predict is this brown peak. What we see are the points, and you can see the points are a bit too high. And for antineutrinos, we predict this orange peak. And here you see the data. There, the statistics are much worse. The interesting thing is this brown peak, this brown histogram is calculated assuming that delta is 0, assuming that CP is conserved, right? The dotted lines allow the delta angle, the angle that parameterizes CP violation, to change. And you can see this dotted line here is a much better fit to this data. And this corresponds to maximal CP violation, the angle being 3 pi by 2, right? And if you look down here, you can see the dotted, the dashed line is a better fit to this data as well. And these plots are taken from an article that was in Nature last April. It was the cover of Nature, saying that these results give indication that CP may be violated in neutrino oscillations. And I'll go through this plot. It basically just shows that the best fit to this data is for CP violation, a maximal CP violation, which is great. But unfortunately, there's another experiment called NOVA at Fermilab, and they don't see any such thing. So we need to better understand our experiment, and we need to build bigger and better experiments. And that's what we're going to do. I'll skip over this because I'm already gone on long enough. We are building a much bigger experiment in Japan called hyperkamiokanda. And to answer the first question that will be asked, I don't know what's beyond hyper. We had kamiokanda, superkamiokanda, now we're building hyperkamiokanda. My grandchildren will build something bigger than hyperkamiokanda, and no, I don't know what they will call it. Hyperkamiokanda is roughly, it's actually 9 times the fiducial mass of superkamiokanda, and we're increasing the power of the beam greatly, and this will give us enough events to really study this. You can see this is interesting, but statistically very ropey. So we need many more events. In this new design, we will have not tens of events, but thousands. We'll also be very sensitive to proton decay, and we'll do all sorts of fascinating astronomy. And we're building it right now. It's been approved by the Japanese government. It is proceeding. We have put in a request for the UK to contribute to this out of the UK's infrastructure fund. We have positive signals that may happen. That's superkamiokanda underneath Mount Akenoyama. This is hyperkamiokanda, which will be under Mount Nijugo Yama, which sounds good until you ask a Japanese what it means, and it's Mountain 25. So not the most romantic name for your mountain. And just because somebody may ask, these are the same off-axis angle. I told you you had to miss the detector by a precise amount. The neutrino beam from J-Park passes halfway in between these two. And so they're both at the right off-axis angle. Meanwhile, the Americans are in the game as well. They're building a detector, an experiment called DUNE. They're building a new neutrino beam at Fermilab. This is kind of their advance beyond MINOS, just as we're advancing beyond T2K, they're advancing beyond MINOS. And so they're building a very powerful neutrino beam. And they're building this really cool, enormous, it'll have 4 of these 10 kiloton modules, well, or some number of these 10 kiloton modules. These huge liquid argon tracking calorimeter. So, you know, we just get little rings from charged particles. They get this kind of detail in reconstructing an event. So this is a prototype of this detector at CERN, and a pi plus hit a proton changed its charge to a pi naught, which made 2 photons, which converted in the detector. So you get this fantastic detail. It's like the world's most, most fine-grained bubble chamber. And from this, they should be able to reconstruct all sorts of things about interactions that we haven't been able to see up to now. And they'll also be sensitive to CP violation. And a question you might well ask, because we get asked a lot, is each one of these things costs $1 billion. Why do we need 2 of them? There's many reasons to that. Since we're here amongst friends and amongst physicists, I'll tell you the main reason we need 2 of them is I never believe anything in neutrino physics that's only seen by 1 experiment. I mean, I haven't gone through all the neutrino experiments that got the wrong answer. There have been many of them. And the reason is these are really hard experiments. And so I don't believe anything in neutrino physics till at least 2 different experiments have seen it. But you can't go to the government and say that. You can't go to the government and say, give me $1 billion to build an experiment, but I may screw it up. So give me $1 billion to build another one. So you need a different answer for why you want 2. And that answer is shown on the next 2 plots. This is the sensitivity to that mass ordering, right? How sensitive are you? So this is the chi-square. The bigger this number is, the more sensitive you are. This is versus how long you've run it. And this is a lousy thing to plot because it depends on a zillion assumptions. But for the moment, we'll just accept it. Okay. This blue curve tells you how sensitive hyperchemiocandea is. And the case that the right answer is the normal ordering or the right answer is the inverted ordering. And you discover not very much. We're on too short a baseline to see this. Dune, on the other hand, is rather sensitive to this ordering. However, if you combine the 2 experiments, you get this pink curve. And you can see it is much more sensitive than either experiment by itself. If you flip that around and look at the CP violation, this is Dune's sensitivity, the green, and this is hyperchemiocandea's sensitivity. And you see that hyperchemiocandea is more sensitive to CP violation than Dune. But if you combine the 2, you still do better yet. They're more sensitive than either experiment. So we need the 2, or one of the very great benefits of doing the 2 is that you gain more sensitivity than you get from either one. There are many other benefits. The biggest benefit would be if we get a supernova, but I don't have time to go into that. So I've gone on long enough. Neutrino oscillations have gone from speculative to routine. They remain the only experimentally confirmed particle physics beyond the standard model. Every angle in that mixing matrix is now being seen by at least 2 different methods and by more than 1 experiment. So now I believe them. We've moved from an exploration and just finding things to an era of precision measurements, and that opens the window for new discovery. There are many other things you can do with neutrinos I didn't even talk about, which are equally important. We still have to figure out the mass hierarchy. I didn't go into that. It's how big is that angle? That I told you that angle between the nu mu and the nu tau was about 45 degrees, but there's a symmetry on either side of 45 degrees. You get the same answer in a vacuum oscillation either side of 45 degrees. So we have to work out which side of that we're on. And we have to look for CP violation. So we have to do this because we won't know what's beyond the standard model until we can be sure what's in the standard model. So we have to work out all of these details in neutrino physics, both to see the standard beyond the standard model, but just to finish up the standard model. So, and the odds are, given that it's neutrino physics and it always ends up being screwy somehow, we'll probably get surprised. So there's much to be done, and let's hope we can do it. And I'll leave you with that. Thanks.
Thank you so much. That was another great talk. I'm really glad that you got 2 spots. There's a lot to unpack there and so many cool experiments to talk about. So thank you. And also thank you for all the historical insights that you often don't get. So especially because they're so personal.
Well, sadly, I'm becoming a historical relic myself, and so So, you know, it's well, when I was young in the field, I always liked it when the old people came along and told us about the old experiments. I remember one lovely lunch I had with Jack Steinberger on at a conference talking to physics teachers in Croatia, where Jack and I were the only two particle physicists there. So they sat me with him every day at lunch, and it was a long chat about the first experiments he did. And he used to carry him in the boot of his car. He would carry him from, you know, he would build them in his workbench in his lab, and he'd stick them in the boot of his car and drive them down to the accelerator. You imagine trying to do that with Atlas. You need a big car.
Big car. Every time CERN gets brought up, I always feel the need to advocate to tell everyone about the summer program, because I know probably because neutrinos is quite, you know, an advanced topic, you have a more mature audience today, but I'm sure that there's a bunch of shy undergrads in there here that aren't showing their faces. If you're an undergrad, you might be eligible to do a CERN summer program. They're so cool. Check them out. I did it. It was amazing. And it's a great opportunity to go and see CERN and also be in Switzerland for a bit. So I just shout out to CERN. Go and check them out.
Yeah, I don't think it probably will happen this summer, I'm afraid, because of COVID, but maybe, hopefully it'll be back the year after that.
Yeah.
And it was also canceled last year, I'm afraid. But
yeah, it's sad. But with everything being delayed, it's likely that the next time it's going to happen, they're still going to be able to go down to the caverns and see the detectors.
I sincerely hope not, but perhaps.
You probably have more insight into that than me, but
yeah, things are delayed, but I don't think they're that delayed. They're not, you know, we're supposed to turn on in the autumn. I mean, CERN is supposed to turn the LHC back on in the autumn. I sincerely hope that it has been turned on by next summer. But CERN is an incredibly cool place, even if you can't go into the cavern.
Absolutely. There's so many experiments that people don't even know about. Lots to see.
Right. Are there any questions?
Yeah. First question. Oh, first we got someone suggesting ultra Kamiokande for the next iteration.
Yeah, we should have learned. I told them at Super K, back when Super K was first proposed, I say, don't go down that line, you're making a mistake. And they laughed at me. But you know, the cosmic ray physicists learned this a long time ago, because they had cosmic rays. And then they built bigger air shower arrays, and they could see higher energy ones. And like idiots, they called them high energy cosmic rays. And then they were screwed, because as they have gone along, they had high energy cosmic rays, very high energy cosmic rays, ultra high energy cosmic rays. No, I can't remember. Extremely high energy cosmic rays, ultra high energy, and on and on and on and on. So now we shouldn't have gone that way. We should have just called it, you know, Kamiokande Plus or Kamiokande 2 or something. But anyway.
Yeah, use like Roman numerals or something. Yeah, there's other options. All right, the first question. What is the reason for using argon as dune despite the complicated nuclear effects?
Well, swings and roundabouts. The drawback of the advantage of a water Cherenkov detector, as you point out, is it's quite simple nucleus. The drawback of a water Cherenkov detector is you can't really work out complicated events. You know, you get these beautiful rings. That's great if you have one. If you have 6, you know, good friggin' luck trying to work out what's going on from all these overlapping rings. And you have a Cherenkov threshold, so you can't see low energy particles. So the advantage of using a liquid argon tracking calorimeter, as in the case of DUNE, is that you can image all charged particles, and you can image very complicated events. In the case of DUNE, that's essential because the baseline is 1,300 kilometers. Our baseline is 300 kilometers. So they're 4 times as far away, which means to be at the oscillation maximum, they have to be at 4 times higher energy. And as you go up in energy, the final states become more complicated. You don't get these events where you have a nice quasi-elastic scattering and a neutrino just turns into a muon and all is well. You get multiple particles in the final state. And to reconstruct those, you'd be hopeless with a water Cherenkov detector. I was actually the chair of the International Advisory Committee that recommend that they build the liquid argon tracking calorimeter rather than a water Cherenkov detector, even though my whole my career in this part of the field has been building water Cherenkov detectors, because a water Cherenkov detector simply wouldn't work for Dune, not on that baseline.
That makes sense.
Yeah, and the drawback of it is, yes, you have a more complicated nucleus, and I didn't go into the details of the nuclear effects and how they bedevil long baseline physics, but I suspect whoever asked that question knows that. And so, yes, they have a harder task of sorting out these nuclear effects. On the other hand, they will have quite a sophisticated suite of near detectors, and they will have 20 years more experience, that has gone on since we started T2K, and getting theorists to understand those effects. So, swings and roundabouts, but I still am quite confident that that having chosen argon will not be the thing that limits their sensitivity.
Mhm.
I hope I'm not proven wrong.
We'll see.
Or else a lynch mob of people in the United States that wanted to build a water Cherenkov detector will track me down.
All right. Actually, how about I unmute people to ask their questions themselves? That way they can ask follow-up questions without having to me go through it. So the next question is from Geoffrey Dormet. I'm going to unmute you if you want. Just let me know in the chat if you would rather not. Someone's asked, oh yeah, just answer. Yeah, the last part is already online if anyone wants to check it out.
Okay. Now, I was just wondering, when you showed a plot with a maximum of the CP violation, where does the limit for the amount of CP violation you can possibly expect to see come from?
If I go back to that horrible formula. So this horrible formula, this angle delta in this matrix is the CP violating phase, and it goes from 0 to 2 pi. So the maximum CP violation I can get, right, is to put this value of delta, is to make sine delta equal to either 1 or -1 for neutrinos and the opposite for antineutrinos. So basically, the maximum CP violation I can get out of this mechanism is to put all the values of this parameters that I've measured, and then make this either 3 pi by 2 or pi by 2, and that will produce the maximum CP violation you can get. That was an interesting thing, because when Minos first did this measurement, this is their final result, but their first antineutrino measurements, when they had very limited statistics, were down here, and the allowed regions didn't actually overlap. And you might have gotten excited at that point and think you'd proven CP violation. But the difference between the two was much, much bigger than you could get from any value of delta. And so that would imply a CP violation, but not from that mechanism. And in fact, if you then look at it, it would imply not CP violation, but CPT violation, which is a violation of special relativity. So then they took some more data and it went away. It went away in the sense that the errors now overlap. It is still true that these central values are different by far more than could possibly be. They're far more than you could get from CP violation from the mechanism I've discussed. But the error bars overlap, so it probably doesn't mean anything.
Great, thank you. I hope that answered the question. The next question comes from George Alexandros. I'm gonna let you unmute yourself if you would like.
Yeah, hello.
Here.
I was wondering on the rings from Super Kamiokande, how does a computer distinguish fuzzy from sharp? Is there a way to quantify it?
Yeah, I didn't mention it, but that plot is actually shown. There's this ring, there's this, my cursor keeps disappearing, this electron muon PID discriminator. And it's basically done by taking a circular ring and putting it on this data and seeing what fraction of the pop, how big can I make that while maximizing the fraction of the hits that are inside relative to outside. And for a muon, I can do that very well because I can put a circle on there and essentially get all of the hits in it. Whereas for an electron, that doesn't work because it's fuzzy. And so when you do that discriminator, you end up with this plot. And this plot, that has that discriminator then scaled such that things which are sharp fall to the right, things which are, unsharp fall to the left. And so these are electrons, right? And these are muons. And the colored histogram, the dots are the data. The colored histograms are the prediction of Monte Carlo. And you see the Monte Carlo, the new mu's are over here and the new e's are over here. And neutral currents, as I said, these days are mostly just background. So they just sort of sit in the middle and prevent you from having a nice little double peaked thing with a hole in the middle. They fill in the bit in the middle.
So you try to fit the circle, and if you can do it in many ways, then it's an electron. Did I understand it correct?
Well, if when you draw, if there is no circular disc you can put on there that contains, if there's no circular line you can put on there where you get all the points in it, unless you make it so wide, right,
Yeah,
that it's inconsistent with the number of hits, then it's an electron. And you may be getting at the fact that, geez, couldn't we do better than that these days? I mean, with all these machine learning techniques, couldn't we do a better job of telling muons from electrons? And the answer is almost certainly we could, but we haven't got there yet. We haven't, we haven't probed that in detail. And the problem is that this lies in the middle of a long and very complicated analysis chain. And doing anything to any part of it, then you'll have to redo all the rest of it. And we have redone the fitter, the thing that fits the energies, and we made huge improvements to that, which is what eliminated neutral current pi naughts basically as a background. But we haven't yet done that to this. And yeah, if we had a really good graduate student who wanted to do that, I'm sure people would be more than interested.
Okay, thanks.
Sure.
Just another reason to learn to code. I feel like some physicists like to be like, oh, do I really need to? And they struggle, but it's so useful nowadays for everything. And it makes you much more employable if you decide to leave academia as well.
Indeed, but I mean, Hyper K is going to be different, but Super Kamiokande has been running for 25 years, and the collaboration shows it. You go to a Super K collaboration meeting, most of the people in the room, remember the Grateful Dead, right? And so the code is all in Fortran, and that inimitable old style Fortran with lots of go-tos and that sort of thing, and 3 comments in 4,000 lines of code. So it doesn't exactly cry out at you that what you should have fun doing is attacking that code.
Oh dear.
We're replacing it all for Hyper-K. Hyper-K, it's being done all using all the modern tools and everything. So don't worry. If you want to work on Hyper-K, it'll be fine. But it is another thing that deters people from going back and trying to apply modern computing methods to this. You want to write a convolutional neural network in Fortran?
Rather not.
Oh, suddenly the volunteers have stopped lining up.
No, maybe more for the future experiments then. Right. Anyone got any more questions? If you put them in the chat, I can unmute you and you can ask it in person. I think that's all of them. Oh, we have another question. Hang on, let me just. There you go. There you go. All right. Yeti downstream, you should be able to unmute yourself. Maybe not. Okay. Not getting anything back from there, but we have another question again from George Alexandra, so I'm gonna let you unmute yourself as well.
Yeah, Hyper-K seems interesting, and if a student wants to get involved with it, how should he approach it?
I've got it now. I'll let you go first.
Okay, thanks.
Well, you apply to do to become a graduate student at some institution that's working on Hyper-K, either in the UK or, I mean, there are Hyper-K institutions all over the world. So, but the obvious way for an undergraduate to be involved in Hyper-K is to apply to do a DPhil, a PhD, depending upon where you go, working at a Hyper-K institution. Oxford obviously is working on Hyper-K, but so are many other UK institutions, Imperial, King's, Warwick, Liverpool, Glasgow, Edinburgh, Sheffield. I'm probably going to piss off somebody by forgetting them. Liverpool, did I say Liverpool? Lancaster, a bunch more. And of course, there are institutions in many countries working on it.
Yeah, I understand. Thank you.
And we will need a small army of graduate students. So.
Great. We have another question.
Do you think we'll ever get to a baseline of across the world or even Earth to the moon sort of territory?
Well, Earth to the moon would be a little difficult because the moon, unfortunately, doesn't stand still.
It does stay pointed at the Earth, though.
Neutrino beams are not something you can really aim. I mean, their direction is set by these enormous concrete structures they're built, so you can't really do that.
Well,
interestingly enough, there was a proposal, a semi-serious proposal to measure the mass hierarchy using a neutrino beam from CERN to Super-Kamiokande. And
awesome.
That baseline is so long that the beam would have to be canted down into the ground at a 45-degree angle. The engineering of that would be challenging because remember, once you collide the protons with the target, you have to allow the pions to decay. And in the case of the beam at CERN, that decay volume would have been almost a kilometer long, canted down into the ground at a 45-degree angle. The advantage of that is that over that enormous baseline, it becomes binary. If you have the normal hierarchy, you will see events. If it's the inverted hierarchy, you won't. And so you only have to run the thing for a relatively short period of time, and you will measure the hierarchy. That, unfortunately, is also a drawback because convincing people to build such a ludicrously difficult and expensive thing and then run it for 6 months and announce you've measured a bit, and it's plus or minus, you've measured a bit, and yay, so shall we say that that was not supported. People have talked about, so what's beyond this? Hyper-K and Dune are kind of the farthest you could imagine going with this kind of experiment. And the reason is because by the time you've built Hyper-K and Dune, you'll have enormous statistics and you'll be down in the grass of the systematics. And the problem you have is, which I sort of alluded to when I showed you how the difference between a neutrino beam and an antineutrino beam, those differences will begin to dominate our ability to measure anything. And you won't probably be able to do any significantly better than Dune and Hyper-K will do. And so the idea is to stop getting your neutrinos from pion decay and instead to build a neutrino factory. So the way a neutrino factory works is you make a pion beam, you allow the pions to decay, but you capture the muons and you put those into an accelerator and accelerate them up. And then you point the muons at a distant target and allow them to decay. And now you can get a completely symmetric, mu plus or mu minus beam that will make absolutely pure beams of precisely known energy, not this broad mess we have now, but a precisely known energy, which is great, but it would cost, I think the last estimate was about $5.5 billion to build such a thing. Such a thing would be on a much longer baseline, probably about 2,000 kilometers. And so there was proposal to build the neutrino factory at CERN and the detectors down in the southern
Hyper-K.
Italy, and so on. No, Hyper-K is much too far away from CERN. But there were quite a number of different pairs come up with Fermilab to the west coast of the United States and so on. But I think everyone is waiting to see what Dune and Hyper-K do before they seriously talk about building a neutrino factory. The advantage of a neutrino factory is it's a stepping stone towards building a muon collider, because you will learn how to build a muon beam.
But is there a worry about what type of rocket it's going through? Because if it goes through the mantle, it's going to behave differently or not?
Yes, there is such a worry. The matter effects I was discussing do affect the beam as it propagates through the Earth. That is why a longer baseline experiment, or one of the reasons why a longer baseline experiment is more sensitive to the mass hierarchy. It's going deeper through denser rock. And so there are systematics that come into these comparisons that arise from your uncertainty in the density structure of the rock you're going through. And those, when the studies were done of the neutrino factory, those were systematics. They weren't the dominant ones. But that would have, if one ever got around to being serious about spending $6 billion to build one of these things, then one would have to look at that in a lot more detail.
So that could become Ultra K.
Ultra K, yeah. The age of
nice
Ultra.
ring to it.
No, he was a bad guy. No. Okay.
If no one else is going to go, I mean, as fascinating as this is, do we know where this is going to get into practical applications as opposed to us philosophical geeks who like weird, obscure things?
Well, the practical applications of the neutrinos themselves, I think, are likely to be minimal. I am not convinced by any of the proposals I have seen to try to build devices, or some people have suggested using neutrinos to communicate between Europe and North America, because since they cut through a core of the Earth rather than around the rim, you can in principle shave off a few milliseconds, and apparently in financial markets, that would actually enable you to make a profit. The problem is that neutrino rates are very low. So whereas the neutrinos go quickly, the information not necessarily so, right? Because your rate of bits per second is low, and so on. However, the we develop technologies in the course of these things which have already been used more broadly, and we, it's like any of these experiments. It's a punt. You measure the fundamental laws of nature, and you hope that they will enable you to break the rules and do profoundly different things than you could do before. I mean, without modern, in classical physics, you could have, spent an infinite amount of money and you can't build a laser because lasers are impossible in classical electrodynamics, right? And so, by breaking the rules, you produce entirely new possibilities. Will neutrinos lead to that? I don't know. But I do know that unless we pursue these questions, right, unless we do these experiments, we'll just be left wondering whether, the matter-antimatter asymmetry arises from this mechanism or not. And, I am okay with people who say, I don't care, right? I don't care what the matter-antimatter asymmetry comes from. I want to get plastic out of the oceans. And I have great sympathy with those people. And I would be prepared to take a public ballot. And if people said, no, we're taking your money away to spend it on environmental causes, then I would accept that decision. But the total amount of money we spend on this in the world, these individual experiments are quite expensive, but there's only a couple of them. And the total amount of money we spend on this in the world simply vanishes in the world's R&D budget. So if you want to get plastic out of the oceans, this wouldn't be where I would go get the money. But, nonetheless, I am sensitive to the fact that we are doing more or less blue skies research. And, and if people don't think that's a good use of the taxpayers' money, I can understand why people would say that.
Well, it's more use than giving it to Boris.
Well, yeah, but that would be true of pretty much any money that the British government spends. So,
on a completely different note, I'm noticing that we've got a completely weird setup of Rembrandt lighting going on all the video feeds. Yeah. Whoever's hosting this is Oxford Physics. You've got a complete Rembrandt lighting with two light sources.
Oh, yeah.
We believe in arts and sciences here.
Dave, you've just got the light from the screen giving a flash shot.
Well, I've been sitting here thinking. You see, I'm facing to the west here. I have a big window in front of me in the west. And when I started this thing, it was all brightly lit. But I should have stopped to think what time of the year it was, and the sun's going to friggin' go down. So now it's completely dark in the room, and so I can go over and turn on the light if we're going to go on. But
yeah, I've got it going on now. I've got the blue light down here from the phone screen and the yellow light from the fluorescent bulb up there.
All right, I think that's a good sign that we've been going on for long enough, and we think we have reached the end of all the questions. Someone was asking about the slides. This video will be uploaded, so that should be enough. But I'm sure if you email Professor Wark, he'd be happy to send them.
There's no
maybe. I'm sure you are easy to find online.
I was just thinking I could post them here. Emailing them is a problem because they tend to be quite big, and then they bounce around in email servers and don't go through. If there's somewhere we can put them, I assume the Physical Society has a website or something that you put.
So we could do that, or you could. Yeah. I mean, you could, if you have them right here as a PDF or something, you can pop them in the chat, I believe, or a link to them or something. But if you don't like have it right there, then you can send them to us, and we can figure out how to put them somewhere where people can find them.
I'll send them to you, and you can find somewhere to put them.
I'll make a note, Michael. If they don't appear somewhere where you can find them, then message us, and we'll let you know how to get them. Great. Well, thank you for all the questions. Professor Wark, thank you so much, both for coming to our conference that we did and giving a talk there, and then also these past 2 weeks. You're a great communicator, and it's a really interesting subject, and definitely people have been interested in it. Sometimes people kind of leave during the questions because it goes on for too long, but we still have a couple here, so thank you to everyone who stayed till the end.
Well, thanks to everybody who stuck around for 3 consecutive weeks of listening to me. That's heroic.
I mean, those are brilliant stories. You don't really get the opportunity that often. And yeah, so let me see. I don't think we have enough speakers for our second year presentations that we would usually do this time of year, but if they do happen, you'll get that on our Facebook feed. And then next week we have a talk on black hole physics, so some cosmology for the people who are into that. And then the week after that, we have more applied physics. We have a talk on biophysics and glacier dynamics, so environmental physics. So if you're interested in more, if you're the person who wants to get the plastic out of the ocean, maybe that's more something for you. But yes, just stay up to date on our Facebook page. I'm about to resurrect our Twitter feed as well. So if you subscribe to that, you'll get that there if that's your preferred method of keeping up with things. Yes, Professor Wark, is there anything else you would like to say?
No, just thanks very much, and I'll see that I'll see that person who asked the question about how to get involved in Hyper-K. I'll see you at a collaboration meeting in a couple of years.
Great. Thank you to everyone, and see you next time. Bye.
Bye-bye.
Thanks, bye.